Okay. So, I remember we finished talking about what a tensor is. So maybe what I will simply summarize is the main formula. And then I will, in fact, go back to our discussion of metrics, because we, in fact, skipped around a little bit the last time. So what is a tensor? Basically, if you take a pragmatic approach, a tensor is just an object that has multiple indices. Right? And what we did the last time was to ask, let me write it down, for A1 through AM, and I think I put a prime on these indices, B1 through Bn. So we have n upper indices, and we have n lower indices, and we have transformed our coordinates from x to c, which means that with I've given you a prescription for every component of x. I have given you how it's defined in terms of c. And now I'm going to ask, how are the components of my tensor T related to each other in the two coordinate systems? And the answer is given by the following. So T, I1 through IN, this is the one in the C coordinate system. Right? And then J1 through Jn. And so this is x. But what you first do is you plug in, for each component expressed in x, you plug in all the x in terms of its new definition in terms of C. And then these are the x indices. So you contract all the x indices with the Jacobians with the x indices contracted with the x indices. So let me write it down and you'll see what I mean. So this is A through A1 through AM, so A1, and this will be X, I1, and then all the way to DCA M dx IM, and then these guys will be contracted with dx J1 dc B1 all the way to dx Jn dc Bn. In other words, a tensor is a multi-index object such that its indices will transform by contraction with the Jacobian, with the appropriate Jacobian. That's basically the kind of lowbrow, pragmatic definition of what a tensor is. And you might ask why, right? So why define a tensor this way? Because the answer is that if you define your tensor this way, you are guaranteed that when you go from coordinate system to coordinate system, you get the same prescription to compute an equation or a physical quantity, right? And if you want to know what the equation looks like in some coordinate system, it's the same way of calculation, no matter what the coordinate system is. And you can check it by, in fact, transforming your coordinate system in this way, and you will find, indeed, yes, if you go from X to C, in fact, this is the same way, same method, same prescription of computing whatever it is. Is it your equation of motion for whatever system you're studying, or some temperature, or some other observable that you're interested in measuring, right? So whatever it is, or some geometric quantity, whatever it is, making sure your tensor transforms in this way is going to ensure that you have the same prescription of computing your equations, your observables, your geometric quantities, and so on, no matter what coordinate system you're in. Okay? That's, in fact, the key behind tensor calculus. One of the key reasons for doing tensor calculus is so that you can do calculus in whatever coordinate system you are in. Okay? So, like I said, I want to go briefly back to talking about the metric. So as I've said before, the metric is for measuring length. So the metric measures distances, or in other words, it's the object that allows you to define what you mean by length. Right? So as you may recall, the distance between x and x plus dx, and now I'm in arbitrary coordinates. Doesn't matter whether x is Cartesian or not, or spherical or whatever. The point is that the distance between them, the square of the distance, is in fact given by the metric gij of x, and then dxi, dxj, where these dx's are the infinitesimal displacements. Okay, so x is here, dx is the middle displacement in whatever coordinate system. And so, if you want to know what's the finite length given 2 points, let's say I have some initial point, xi, let's call it x of lambda 0. So I'm going to I will need to parameterize the starting point to the ending point by one parameter. Right? It's basically a coordinate x of lambda. Lambda is now the coordinate on this line, so that by the time I reach the other endpoint, let's call it x final, is now x of, say, lambda 1. Right? So in other words, lambda runs from lambda 0 to lambda 1. Actually, very often I just like to call it 0 to 1, right? So that I don't have to remember what the endpoints are. But if you choose a path, then this will immediately tell you that dl, the total length, of course, is just the integral of the infinitesimal. But now we have a parameterization that allows you to do the calculation. Whenever you want to do a concrete calculation, you need coordinates. It's always the case. You can't run away from it. So that's why we need to choose a lambda, one parameter coordinate, to tell me where the path is going. Because obviously, this length is going to be different from this length, for example. And so I need to specify precisely which path I'm looking at. So if I plug this in, this is, let's do it step by step, right? So gij, x of lambda, and then dxi, dxj. But right now it's still a little bit abstract, right? So I have these infinitesimal displacements. So what I need to do is I need to write them as velocities. Right? So I have dx d of lambda, but because of these d lambdas, I need to put the d lambda outside. And so this guy will be cancelled out by this guy. But now in this form, I have now a concrete integrand as a function of, this is now a function of lambda that I can integrate from lambda 0 to lambda 1. So that's the first thing I want to say, that to figure out the actual length of a path, you first have to tell me what the path is, then you give it a coordinate, from one point to the other. By the way, the length doesn't matter whether I call this the initial or the final, right? It's just a number. So I can integrate from here to here or here to here, doesn't matter. But I've just chosen to you have to pick one, right? This is not the only way to describe length. So it turns out that there is one other way using what's called the affine parametrization, which you would work out in your homework. So you're going to prove that you first understand. First thing you need to do is you need to understand that this length, this definition of length is independent of the choice of lambda. So I think I've said this before, it would be very strange if physics or geometry somehow depended on the coordinates we use to do the geometry or the physics. Because coordinates is a human construct, right? It's somehow it's just easier for us to do Cartesian or spherical or something like that. But the nature or geometry, right? It is something intrinsic that's objective. It shouldn't depend on our definition of coordinates. So this is one check that it in fact doesn't. If you change your coordinates from lambda to say lambda prime, then you will discover that I can write down the answer immediately. Well, you need to tell me what the new endpoint is, so I'll call it lambda not prime. What's the new endpoint? Lambda 1 prime. But then the rest will just be exactly the same. Gij, I assume you now know what is x in terms of the new coordinate lambda prime. And then you'll be now dxi, d lambda prime, dxj, d lambda prime, and then d lambda prime. So you see, I didn't have to think. Why? Because I know that this thing is independent of whatever coordinate system I'm using. But I can check explicitly, right? So I can, in fact, carry out the calculus. You know how to change variables over here. You know how to change variables over here. So you can check explicitly that you do, in fact, recover this expression upon changing from lambda to lambda prime, which means it verifies this statement that length, as I've defined it here, is in fact independent of my choice of this coordinate, the one-dimensional coordinate I use to parameterize the path. That's the first thing. The other thing related to affine parameterization that's more related to it is the fact that once I recognize that, then I can choose a particular choice such that the square root becomes a constant. Gij x dot I, so dot means the derivative with respect to my lambda prime, x dot j becomes a constant. Okay? So this is your homework. You will figure out. It's not difficult once you know what you're doing. You basically are arguing that upon a change of variables, you will discover a differential equation because you want this to be constant. So the question is, what is that differential equation? And once you've identified the differential equation, then basically you can argue because the solution can always be obtained by integration. I just need to check because I'm doing it manually that the thing is still running. Okay, still another 10 minutes. Because the differential equation solution can always be obtained by integration. So therefore, the solution always exists, and therefore you can always do it. Okay? So you are going to discover that for your homework. The reason why that is important in turn is because that once you have recognized this new form of parameterization, the affine parameterization, then it will allow you to in fact write this length in a different way. And in fact, you will now write not the length, but the square of the length. You have a question for me? Don't be shy.不用害羞。
我可以用中文。
Yeah.
那个底浪打是怎么从你 刚才那个 L
This
dl
one?
平方不是中间的，
This one?
是从你刚才 dl 平方
Yeah.
那里导过去。
Yeah, so you understood if I just write this, right?
Yeah.
So all I'm doing is that I'm using lambda as a parameterization. So instead of dxi, I now write dxi over lambda, and then instead of dxj, I have dxj over lambda.
Oh.
But you have two powers of d lambda in the denominator, right? So I need to cancel it out using the d lambda outside. Yeah, yeah, yeah. There is an assumption that d lambda is increasing. Yeah, it's positive. Yeah, but otherwise, you need, again, the key point is you need a coordinate to make the integrand explicit. Right? You need it to become a function of lambda so that you can actually integrate it. In fact, very often you can't do it analytically, but you can do it by hand. So if you have a path, you really need to know its length, you can at least put it on the computer. Right? And the way to do it on the computer is you compute this quantity, and then you do it over little segments, right? And then you just sum it up. Okay. So, like I said, once you have recognized the affine parameterization, you discover a different way of parameterizing your length. Turns out that it's easier to do it from length squared instead of length. And what you discover is that it looks like this lambda 1 minus lambda 0 times integral from lambda 0 to lambda 1 d lambda, and then in fact it's gij x of lambda, and then dxi d lambda dxj d lambda. So again, now I'm assuming lambda is affine. It's not always true. Okay, so this is something that I need to emphasize. It's not always true that your parameterization is affine. Affine means the definition of affine parameterization means that you have chosen lambda such that the square root here is constant. Well, by the way, if the square root is constant, so obviously the inside is constant as well. So in fact, this is constant. So if there's constant, you don't have any integrals to do, in fact. Anyway, you will show, in fact, why this is true. Right? And you will discover that starting from this more general definition, if you choose this constant, let's call it C. Okay, then you will discover that that guy can be written in terms of the lambda 1, lambda 0, and C. Okay, so this will turn out to be a function of lambda 0, lambda 1, and C from over there. You discover this for yourself. This is a homework problem. But I claim it can always be done. And in many situations, this turns out to be very useful. Okay. Any questions for me?
So
Yes.
L is originally defined by another coordinate, and we want to find a new coordinate called affine parameter parameterization so that
originally it was this coordinate.
yeah.
Yeah. And so strictly speaking, I should put a prime on it, but I don't like to put too many primes on it, right? So when I switch from lambda to the new coordinate lambda prime, where lambda prime is affine, then it takes this new form. Yeah. It's not obvious how right now. It's not supposed to be obvious how this formula can be related to this formula, but I claim it is. And the key is that you are able to set this to a constant. Okay. You should find it out for yourself in your homework. So you discover in my homework, I don't like to just give problems where you compute something. Sometimes I do that, right? And so because of course we need to know how to compute some things, but sometimes I also like to make sure that you can step through some of the intermediate arguments yourself, because after all, what's the point of getting an education? The point of getting an education is to get you to think, right? And so they say your teacher telling you, here's the fact, here's the reasoning done for you. I think very often it's much better for you to step through the thinking yourself. I think that's the way to learn, for one thing, right? But it's always very important. Think for yourself, right? And it cannot be overemphasized. The importance of thinking for yourself. Okay, so closely related to the length are things like angles. So what do I mean by that? So here we have a finite path, but previously we talked about tangent vectors as well. Right? So let me begin with that. So the length and the angles related to tangent vectors. So let me just remind you of some vector calculus. So if you are in flat space, doing vector calculus, then remember that if I take v dot w, that is what? That is actually the length of v, length of w times the cosine of the angle between them. Right? So this is, v is pointing this way, w is pointing this way, and this is the angle theta. This is the dot product, in fact, gives you the, not just the length, but also the angle between these guys. Right? So in particular, if you divide by the length of v and divide by the length of w, you do in fact get the angle. So I claim that in fact, in curved space-time in general, even though our emphasis is not to do curved space-time itself, but to basically set up a formalism that allows you to do that if you need to, using the metric basically, you can do basically the same thing. The generalization is Gij Viwj. So remember that we're using this summation convention. So whenever you have a repeated index I, you're summing it over all the dimensions that you have. And when you have j, also now repeated, you're also summing it over from 1 to 2. And this is basically the analog of the dot product. By this arrow, I mean analogy, analog. Okay. And now I want to kind of build my way up to this definition. Why it makes sense. So one of the ways to understand this is to invoke a result that I think is fairly intuitive if you think about the surface of the Earth as an example. So as we know, human civilization took a long time to recognize that we live on a curved surface. Right? Actually, even to this day, there are some little cuckoo people who think we live on a flat Earth. And I'm not even kidding, we have the internet now, and we still have people who think we live on a flat Earth. How do you know? You go on the internet and you type in flatearthers.org, and you will find there are a group of people out there who think, yes, the Earth is flat. I don't know how they can live with themselves, but anyway, they do. But yeah, so it's understandable. If you don't have the technology to travel far, you don't have the technology to go to space, then I think it becomes understandable, right? How do you know whether we humans, very, very small compared to the size of the Earth, how can we tell whether or not we live on the surface of the planet? Right? So we're very small, we're roughly, at most, you're what, 2 meters. Right? The tallest humans are, you look at all those basketball players, right? Maybe slightly taller than 2 meters. But then the Earth's radius is something like 6,000 kilometers. Right? So we're small, even if we're very tall, we're still very small compared to the size of the Earth. So the point here is the following, that in fact it's very difficult to do so unless you can go to space and you take a picture of the Earth. Or, as I discussed before, the experiments you can do. You try to draw parallel lines and see whether they meet, or you try to parallel transport vectors and so on. But these experiments are easy to describe, but very, very difficult to do in practice. Right? And of course, eventually, what happened was that you have people like, there are people who started to build ships, and they eventually found a way to circumnavigate the globe. Right? So you don't have to do these differential geometry experiments. You just take the boat and hope that you get back to the same place, and indeed they did. But why am I saying this? Because when that teaches you that if you are very small and your attention is confined to only a very small patch of your local space, then whether or not you live in a flat or curved space will hardly matter to you. Right? So what I'm trying to say is that space looks locally flat. Let me put in quotations because I'm being heuristic here. I'm being rough and intuitive here. And you can make it precise. And here's, I'm just going to write down the formula there. So what I'm going to do is I'm going to call this point y naught. Let me use the same notation as I use in my notes. Yes, I call it y naught, yeah. So I'm going to use a coordinate system I'm going to call y, because my x is the arbitrary one. But I'm switching to y because I'm going to use that to denote the coordinate system where, as I set y approaching y naught, my metric will in fact go to the flat line. What's the flat metric? It's just a Kronecker delta, as I've explained before. Right? So what it means is Gij of y, as y goes to y naught, will in fact begin at 0th order as Kronecker delta. Remember, when you have Kronecker delta and when you're using Cartesian coordinates, this just basically comes down to Pythagoras theorem. And then you have minus 1/3, followed by the Riemann curvature tensor, which in this course I'm not going to worry too much about. Okay? But I do want to mention again that it does in fact contain the local information regarding whether your space is curved or not. If your space is flat, Riemann is 0, so it would just be Kronecker delta. But if your space is curved, then this will be non-zero. Let me just write down the answer. Y minus y naught, the nth component, y minus y naught, nth component. And this is an infinite series. You should think of this as basically a Taylor expansion. Right, so this is basically a Taylor expansion. Okay. So now all I have to do is choose such a locally flat system, and now I consider VIWJ, GIJ. But if I evaluate it at Y0, what happens? All these terms will go away, and I'm left with Kronecker IJ, VIWJ, which is in fact nothing but V dot W. In other words, you recover, because now you are in flat space, you recover your vector calculus definition of the dot product by going to a locally flat system. And that in fact justifies that this object here, which I can just define to be V dot W, but now not in the vector calculus sense, but in this sense, can